So we previously noted that compound interest is definitely the best kind of interest out there. Now we're going to look at what goes on when your interest is compounded more often than once per year. In fact, most savings accounts that you might have, although the interest right now is nothing, they would probably be compounded monthly, some quarterly, and so on and so forth. So if you look at this second paragraph here, it says, so let's say that interest is being compounded 4 times per year. We would say that quarterly, so every 3 months, a portion of that yearly interest would be deposited into your account. So if we go back to that initial investment of $600, that's a P equal to 600, that principal. An interest rate of 5%, so as a decimal, that's 0.05. The bank would not add 5% to the account 4 times per year because they'd be giving you more than 5% interest over the entire year. They instead divide the amount of interest they give you into 4 equal payments. In other words, they pay you 1.25% every 3 months. How did they get that? Well, they took the 0.05%, they divided it by 4, and that gets you 0.0125. So if we were to calculate the first payment after 3 months, we would take, ignore that extra writing I have there, we would take this 600 times 1 plus 0.05. If we're doing that for the full year, we would write this as a raised to the 1 power. But we're going to divide that part by 4, and here within 3 months, we would have given you that 0.0125 of the money as interest. So this calculation becomes this, and using Desmos here, we would now do 600 times 1.0125, and we would get that you would be depositing $7.50. In other words, the account balance after 3 months becomes $607.05. So what happens after the second set of 3 months? In other words, halfway through the year, how much would we do? Well, we would do another one of these deposits. So we would take the 607.50 that is currently in your account after the first 3 months, and we do another 1 plus 0.05 divided by 4 times that to get the next 3-month amount. Because since we're compounding the interest, you're going to get to earn interest on that $7.50, albeit it's not that 5%. Remember, it's the 0.0125. So let's get that calculation. Notice when I do this, I can just multiply my previous result by that 0.0125, and I get now the amount in the balance after 6 months. So that's 615.09 if we round it to the nearest cent. That's what we're looking here. So going back to the course spec, it says, oh, so we did that calculation in number 1. Then we shoot down to number 2, and it says by the time the first year's up, the interest would have been calculated 4 times, because we are doing this quarterly and we're adding in interest 4 times per year. So the total exponent on the parentheses in our future value calculated would also be 4, which is the number of times per year that the interest has been compounded. In other words, if we took that formula we were given prior to this, that compound interest formula, it looked like this. A equals P times 1 plus the interest rate raised to the time. We're now going to change this to A equals the principal times 1 plus the interest rate divided by the number of compounds. In this case, that number of compounds was 4. And we would raise it to the number of compounds per year times the number of years. That's what the new equation would look like. So if we go back to the course spec here on 3 says, if interest is compounded monthly, that means you're compounding 12 times a year. After 60 years, you would have, or after 5 years, you would have done 60 compounds. And then in general, if we compounded t years, and we had n compounds per year, maybe daily, maybe minutely, maybe every second, we would compound it n times t times a year. So let's generalize this real quick. That might have been kind of confusing. Definitely ask your instructors during your live live access time on big blue button if that for more explanation of that if that was getting a little confusing. So here's the generalized equation. We now take the interest rate, we divide it by the number of compounds per year, and then we raise all this to the number of compounds per year times the time. So here's a reiteration of what all the letters mean. And we're going to now use this formula probably more so than the previous compound interest formula. So let's apply this now to a specific problem. So we're going to use the compound interest formula to calculate the future value of our 600 invested at 5% interest compounded quarterly for 10 years. Well, as I've mentioned before, make sure you identify all the information that's given. So the 600 is the P. The R, hopefully you're getting sick of me writing it, is 0.05. That means you're remembering it. And the compounds, the N, which is number of compounds per year, quarterly here means 4 times a year, and then our t turns out to be 10 years. So if we want to calculate the future value, we would just do A equals P times 1 plus R divided by T raised to the NT, and just plug in our values here. So A represents the future value. Replace P with 600. Do 1 plus 0.05 divided by 4 raised to the 4 times 10 power. Skipping over to our handy Desmos, we're now going to type that in and see what our result is. So 600. Notice I'm using parentheses for this. You don't have to. It's also because I'm typing in the sum part, so the plus 0.05 divided by 4. Again, you don't have to do that, but it is helpful. Now, if you are still using your cell phone and are not on a laptop, to get that exponent, you need to do A to the B, and then you need to put parentheses to ensure that the calculator does 4 times 10. If you don't do that, it'll raise it to the 4th power and then multiply the entire result by 10. So notice our new amount is 986.17, raising it to the nearest cent. That's how much would be in our bank account at the end of the first year. Let's compare that to the compounded just once per year and see how big of a difference is it. So if we do once per year, we would divide the 0.05 by 1, and we'd raise this to just the 10th power because we're only compounding once per year. Notice not a huge difference, right? 986.17 versus 977.33. What? That's $9 roughly, a little less than $9. But remember, you didn't actually do anything. All you did was put it in a different savings account. So let's do a couple more iterations of this. What if we compounded that same amount of money monthly? So keeping everything the same, P equals 600. The rate is 5%. The time is still 10 years, but we're going to do an N of 12 because we're compounding monthly. That means in 12 times per year. So replacing all those pieces in our formula, we end up with this. And then that second one, what if we compounded it daily? So let's add that one in, and then we'll do both in Desmos all at once. So the same P, the same R, the same T, but now our N equals 365 because we're using 365 days in a year. Actually, there's 365.25 if you account for the leap year, but for now, we'll ignore that. So here comes this calculation. And let's plug all this mess into Desmos and see what kind of values we get. So what I'm going to do is go back to this previous one where I had the 4, and I'm just going to replace the 4 with 12, and I'll get the monthly compound. And now we're getting 988.21 approximately. I'm also going to duplicate this because I want you to be able to see how that changes. And so now I'm replacing the 12 with 365 and the 10 with 365. And we'll see how much more do we get. Oh, look at that. Almost $1. Well, slightly over $1. 989.20 if we round to the nearest cent. So while it is better to have more compounds per year, you can see it doesn't make a huge difference. I mean, they're depositing interest in your account every day on this one, and here they're doing it every month, and we get slightly less than $1 extra in interest. This is the section that won't quit. So we're going to move on to a slightly different case or look at these things, and that is how are we going to be able to compare these different compound interest rates so that we can see which one's the best maybe in an investment opportunity or in terms of a mortgage, which is mostly where this comes from. So the number of times interest is compounded per year does have an effect on how much interest is actually earned. It's not huge, but it is different. And the longer you take out a loan, or the longer things are compounded, the bigger the difference will be. So we need some way to determine which compound interest rate is the best. So we developed this effective interest rate. So first, let's define it. And this definition is crazy. So the effective rate, or the effective interest rate, we can also call that the annual yield, or the APY. It's the simple interest rate which would yield the same future value over 1 year as the given compound interest rate. Note the compound interest rate, we sometimes call that the nominal rate. So what does that mean? Well, if we have two different compounds interest rates, and we want to compare them directly, we just convert them into a simple interest rate over a 1 year period, and we can compare those two numbers directly. That's all this is doing. Caution, you cannot compare simple interest rates to compound interest rates. In the long run, compound interest rates are always better than simple interest rates. In the short term, not necessarily. All right, so here's the formula to convert it. And we've defined a few things here. E is the effective rate, so that's the simple interest rate equivalent to the given compound interest rate for a 1 year period. And then N and R are the same thing as before. R is the number of compounds per year, N is the number of compounds per year, and R is the compound interest rate, or the rate. So let's do one here. A loan has a nominal interest rate, notice that means compound interest rate, of 4%. And the interest is compounded weekly. Okay, so we're going to do calculations. Ignore this. So would you expect the effective interest rate to be higher or lower than 4%? Well, I'm going to say higher because we're compounding every week, so we're going to be earning interest on interest each week, albeit a small amount. Well, let's calculate that effective interest rate. Notice the things they gave us. They gave us the R was 0.04. They gave us the N was, oh boy, I don't know how many weeks are in a year. I forgot. So I'm going to say, well, no, I did remember it's 52. And that's actually all we need. So the formula is the effective interest rate, E, is equal to 1 plus the R divided by the N raised to the N power minus 1. So let's just replace those things, and then we'll dash over to Desmos and calculate it. Oh, fail. This should be a 52, not a 12. We should be putting a 52 here, and then a minus 1. Boy, can you all read that? I switched pens, and that's a wreck. Let me rewrite that. Oh, come on. Epic fails here. All right, so this is 1 plus 0.04 divided by 52 raised to the 52 power minus 1. That's what we're going to smash into Desmos here. So here goes. We need those parentheses, 1 plus 0.04 divided by 52, and then I have a shortcut. I just do Shift 6, and it immediately becomes an exponent. You could always hit the AB button, and then minus 1 there, And there's our effective interest rate. Now, I'm going to keep several decimals here. I guess I'll round to 4 decimal places. In other words, I'm going to round to this 4, right, that 7 right there. So since the 9 after the 7 is larger than 5, I'm going to add 1 to 7, and I would round this to 0.0408. When you're working with these effective interest rates, you need to make sure you include a bunch of decimal places in order to see the difference. Now, as a percentage, this is 4.08%. Now, what is that percent? So let me write it as a sentence. What we've just discovered is that 4% interest compounded weekly. I know I spelled that word wrong. Pretend there's an N next to that U. 4% interest compounded weekly is equal to, or maybe we should say this, earns the same amount as a simple interest rate of 4.08% over a 1-year period. So after 1 year, the 4% interest compounded weekly would give you the same amount of money as a 4.08% simple interest rate. So let's do that calculation real quick and prove it to ourselves. I'm a little scared that it won't work out, but let's just do it anyways. And then if I'm wrong, we can all laugh at me. So here's the compound interest rate of 4%. We said it was weekly, and we're doing it a 1-year period. So we'll calculate that in Desmos. We're claiming that this is the same as the simple interest rate of, remember that simple interest rate, P plus P times R times T here, which is 1. These two values should be approximately the same. Now I say approximately because remember we rounded this value, so it won't be exactly the same. So here we go, switching over to Desmos, and we're going to do the 600 times the 1 plus 0.04 divided by 52 raised to the 52nd power. So at the end of that 1-year period, we would have $624.48 approximately with that interest rate. Let me not copy that. And here comes the simple interest rate. Times 0.0408. And we get 624.48. When rounded to the nearest cent, we get the exact same amount. In fact, if we started putting in the 794770048, in other words, if we put in all of the decimals that Desmos gave us up here, you can see these are exactly the same numbers. So we now know what the effective interest rate does. It allows us to convert a compound interest rate into a simple interest rate to look at what happens after 1 year. So it's only valid for a 1-year period. And then we can see which one earns more money just by seeing which one is the larger simple interest rate for the 1-year period. So let's flip the page and look at page 225. Here we are comparing, asking ourselves, which is the better investment? So here we've got 6.2% compounded daily, or 6.25% compounded semi-annually. So let's write down what these two things are, and then we'll calculate the effective interest rate of both. So the first one, we've got an R of 0.062, and the N for compounded daily is 365. For the second one, that R is 0.0625, and then if you didn't know this, semi-annually means twice a year. So with the effective interest rate, we're just going to plug each of those in. So 1 plus 0.062 divided by 365 raised to the 365 minus 1. We'll get what that value is. This will be a simple interest, an equivalent simple interest for a 1-year period. And then the same thing over here. 1 plus 0.0625 divided by 2 raised to the second power minus 1. Let's see what these look like in Desmos. So here goes. You know what? I'm just going to copy this one, and then I can plug in the, no, that's the wrong one. I want to copy this one, and then I can plug in the values I want there. So let me clean up all this other mess. So notice in this formula, we could care less how much you're investing or how much you're borrowing. That actually has no effect on the result. So that one that was compounded daily, 0.602, gives us 0.063956. So just a little bit over 6.2% simple interest is coming out to about 6.4% as simple interest. And then the semi-annually of 0.0625. Make sure I get my 2 in there. And there's the other one, 0.63476. So I'm going to write these numbers down, and I will round out to like the 5th decimal place, just to ensure I have enough decimals to directly compare these. So that first one's 0.06396 approximately, and that second one is 0.06346. So let's switch back and compare these two. Remember, if we want to turn these decimals into interest or percents, we'd multiply by 100. So this is 0.6396%, and this one's 6.346%. So the compounded daily is just a little bit better if we were investing. If we were borrowing, this one would be better because we want to pay less money in interest over a 1-year period. So folks, on page 227, we're going to get the last piece of compound interest. And our author does kind of a crazy thing. He more or less asked you to learn some calculus. So I did this in a previous class where I showed students taking the limit. And I had students calculating this 1 plus 1 over u to the u power. And as u got larger and larger and larger, the number became closer and closer to a specific number, approximately 2.78. It turns out it's a really special number. It's the number e. E is like pi. It's irrational. It goes on forever and ever. If you look at your calculator, there's an e number there. And we use this when things are compounded continuously. So let me real quick show you e in Desmos. If you just type e in Desmos, it gives you a number, and you might be like, what? And now you know why. It's called Euler's number. It's the guy that discovered it or invented it, whichever way your philosophy is. So the formula then becomes, for compounded continuously, a PERT. If you all remember that shampoo, PERT Plus, you will never forget this formula. That's how I have memorized it. So the P, the R, and the T, and the A are all the same thing. Future value, principal, interest rate, time. It's just we now use E as an exponent. E is a number. That goes in there. So let's flip the page and we'll do a calculation of compounded continuously just so you can see how that happens. You'll be looking for this word specifically as you're working through problems in Connect Math for when to know to use that a PERT one. So let's identify the things we have. We're supposed to find the future value. I'll just say we're looking for that of a 20-year long investment. So we're doing this for 20 years, and we're plunking down $5,000, and it earns an interest rate of 0.04 or 4%. So we'll just take the A equals P times E raised to the RT and plug in the pieces we just have. So our future value is equal to 5,000 times the number E raised to the 0.04 times 20. Skipping over to Desmos, we'll type all this in. So we've got 5,000, and I'm just going to hit the letter E in the calculator or on my keyboard here. And then you need parentheses in that exponent to make sure that multiplication comes. And there it is. You get 11,127.70 cents for things that are compounded continuously. I'll be honest, I don't think I've ever heard of a bank account that compounds interest continuously. Where this mostly shows up is things like radioactive decay, um, or other like elements in the natural world that are decaying. Congratulations, rock stars. We have completed 3.2. Let's review what we learned. In other words, this is the reference sheet if we were all in class, in-person class. This is what I would be telling you to put on your reference sheet. So first off, we learned what compound interest actually is. And I'm going to say it is interest earned on both the principal and interest. And this, I don't know that I said it explicitly, this is an exponential relationship, which is why it is such a better form of investment than the simple interest, which you may recall was a linear relationship. We have three formulas. A equals P times 1 plus R raised to the T. This is the useless one. This is interest, compound interest in a year. Okay, let me try again. Epic fail here. This is interest compounded annually. So it's a very specific case. It's just when you do it once per year. The second equation we looked at, or sorry, the second formula we looked at was this one where we included the N, and this is interest compounded in times per year. And then the last one was the one we just looked at. A equals P times E raised to the RT. This is interest compounded continuously. So what you're looking for in problems that you're going to be working on Connect Math is, does it say compounded annually? If it does, then you would use this one. Note that in compounded annually, what we're saying is the N of this formula equals 1. So if I plug in a 1 here, I end up with this formula. So I would say just ignore this one entirely and always use this one, and note that annually means N equals 1. And then if it says compounded quarterly or monthly or hourly or secondly or any of those different options, compounded a certain amount of times per year, you're going to use this one. And finally, if it says compounded continuously, you're going to look at that one. We then had the effective interest rate, which was a way to compare these types of interest rates. And so that was E equals 1 plus R divided by N raised to the N minus 1. This converted, so converts compound interest rates, not the continuously one, by the way. There's a different formula, but we're going to ignore that. So converts compound interest into simple interest. And it's looking at over a 1-year period. Remember, this was the way we could compare different compound interest rates and compound times to decide which is the better for an investment or for, say, a mortgage or borrowing money. So happy studies. I hope you all are surviving.